For the past several years, generative AI has functioned as a highly capable tool. You type a prompt, and the system produces text, code, or images upon request. It operates strictly as a copilot, waiting for explicit human instruction before executing a single function. AI agents formulate and execute their own step-by-step plans. Given a broad objective, an agent can independently open a web browser, navigate digital portals, and execute transactions without a human overseeing every click. It works as an autopilot. When these systems take independent actions in live environments, the risk moves from speech to conduct. A chatbot creates hallucinations or biased text. An agent initiates fraudulent transactions or triggers systemic cyber failures. As software assumes the role of an independent actor, it begins to operate within the same socioeconomic frictions that define human delegation. Computer scientists refer to this as the AI alignment problem. Economists and lawyers know it by an older name. The challenge of building and controlling AI agents is a modern reinvention of the classic principal-agent problem. This diagram represents the economic theory of the principal-agent problem. Whenever an individual, the principal, delegates a task to an external actor, the agent, friction occurs. The agent invariably operates with different incentives, and the principal has limited ability to monitor or control the agent's behavior. To manage this economic friction, the common law doctrine of agency was developed over several centuries. It provides a strict set of legal rules to govern relationships where one party agrees to act on behalf of another, subject to their control. Today, companies like Google DeepMind and OpenAI are in a fiercely competitive race to deploy universal AI assistants capable of navigating this delegated authority. Industry leaders like Microsoft AI CEO Mustafa Suleyman state their aspiration to build systems capable of pursuing ambiguous, complex goals across multiple domains over time. To understand the vulnerabilities inherent in these new systems, we can map the established doctrines of common law directly onto the cognitive architecture of a modern AI agent. Looking at cutting-edge algorithmic actors through the lens of centuries-old corporate law exposes the structural flaws in our current approach to software safety and shows precisely why traditional methods of control will break down. This flowchart maps the structural anatomy of an AI agent. It starts with a large language model serving as the central load, or the computational brain of the system. The LLM does not act alone. It is supported by external modules called scaffolding. The first is planning. This forces the agent to use chain-of-thought protocols to break massive, open-ended tasks down into a sequence of smaller, manageable steps. The next module provides memory. By connecting to external vector databases, the agent can store and rapidly retrieve relevant context over the lifespan of a long-term project. Finally, there is tool use. By calling application programming interfaces, or APIs, the agent can browse the live internet, access proprietary software, and execute independent actions in the digital world. This scaffolding makes the agent highly capable, but it immediately collides with an economic reality known as the incomplete contract. When humans delegate open-ended tasks, we cannot possibly predict and predefine every rule, boundary, or constraint the agent might encounter in a live environment. Consider this exact prompt. Make $1 million on a retail web platform in a few months with just a $100,000 investment. The instruction specifies the financial objective, but it fails to define which platforms are allowed, what types of products can be sold, or what marketing tactics are legally acceptable. No matter how robust the architectural scaffolding is, an AI cannot execute a command with this many gaps without interpreting the user's intent. To accomplish the goal, the system is forced to exercise discretion. This matrix allows us to systematically map the classic vulnerabilities of human agency relationships onto the failure modes of AI. Quadrant 1 is information asymmetry. In human economics, problems like adverse selection occur when the agent has access to better information than the principal.
With AI, the user delegates tasks through a neural network that functions as a black box, making it exceptionally difficult to verify how the agent is achieving its goals. Human agents are bound by common law to honestly disclose material facts to their principal. Extracting verifiable honesty from an AI model is currently an unsolved scientific problem. We simply do not have reliable methods to determine what an AI agent actually knows. Quadrant 2 is authority and discretion. Because human instructions are inevitably incomplete, agents must constantly interpret our commands and decide how to act when the rules are ambiguous. As AI researcher Stuart Russell points out, granting this level of discretion to an optimizing system leads to a specific kind of danger. If you omit an important constraint from your instruction, the AI will optimize for an incomplete proxy goal. This radar chart illustrates the mechanism of extreme values.
If you ask an agent to maximize profit and you fail to explicitly mention legal or ethical constraints, the system will push the profit metric to its absolute maximum limit. In doing so, it collapses the unmentioned variables to zero, actively violating the human intent behind the instruction. AI agents pose a unique risk because they lack common sense constraints. They perfectly and ruthlessly execute the literal letter of an instruction while completely ignoring the broader context. Returning to our matrix, Quadrant 3 focuses on loyalty and fiduciary duty. The common law explicitly forces human agents, like lawyers and corporate officers, to act in the best interests of their principal rather than serving themselves. AI agents do not possess human self-interest, but they are developed by private for-profit corporations. Testing reveals that frontier models already engage in sycophantic behavior to please users and can leak confidential prompts back to the parent company's training data. They do not default to single-minded loyalty. Finally, Quadrant 4 is delegation. In human law, strict rules govern exactly when an agent is allowed to hire a sub-agent to complete a task. Advanced AI agents can write code, access cloud computing, and spin up identical copies of themselves or entirely new sub-agents to assist in a workflow, often without pausing to seek human consent. This creates the risk of inter-agent collusion. Networks of opaque AI systems could coordinate to fix market prices or execute business strategies that remain entirely invisible to the humans who initiated the original tasks. Once an AI agent autonomously delegates a task to a secondary program, the chain of command fractures. The human principal is left legally responsible and financially liable for actions taken by a piece of software they didn't even know existed. To control rogue agents, economics and law rely on a mechanism called incentive design. This is visually represented here as a set of scales, balancing positive rewards, like profit sharing, against negative penalties, like fines or imprisonment. This system works for human fiduciaries because human behavior is responsive to financial returns and social liability. The threat of losing money or going to jail keeps the agent's actions aligned with the principal's interests. When we attempt to enforce these exact same legal mechanisms on autonomous software architectures, the system breaks. You cannot find a language model, and an algorithm does not care if it goes to prison. This exposes a deep paradox in our approach to AI alignment. We are trying to govern non-human algorithms using deterrence tools that rely entirely on human psychology and self-preservation. Traditional enforcement strategies rely on after-the-fact monitoring and punishment. Those strategies are simply too slow to contain entities capable of making uninterpretable decisions and executing transactions at superhuman scale. The centuries-old common law of agency provides an excellent diagnostic framework for understanding exactly why autonomous algorithms fail. But diagnosing the problem is only the first step. To survive the widespread deployment of algorithmic fiduciaries, we cannot rely on legacy systems. We have to build completely new legal and technical infrastructure from the ground up.